I'm Alan Davis, a software engineer, a former cardiac nurse, and a senior lecturer in health data sciences at the University of Manchester. My goal on this channel is to make health data science, AI, and digital health understandable for clinicians, researchers, and anyone else who's interested in learning about this technology. In this video, I'm going to talk a little bit about the apply functions in R and how these relate to concepts such as iteration and vectorisation. So just before we delve into the apply function, it might be worth just recapping what iteration actually is. So we use iteration in programming languages like R and Python and other languages to do a couple of different things. We can use iteration to repeat blocks of code a number of times or until a certain condition is met, but we also use iteration to go through collections of data structures, for example, to process them in some way. So it might be just to display them, or it might be to carry out some kind of check or calculation on those data structures. So I'm going to focus on the apply functions, but I'm also going to relate this back to alternatives as well. So how you can do this with for loops, for example, and using R's vectorisation as well. So when I talk about vectorisation, what exactly do I mean by this? So for a simple example, let's switch to a different language for a second. Let's look at Python. So let's say we have a list of numbers like we do in this case. So I've got some numerical values stored in a data structure, which in Python is called a list. So I've got 12, 6, 8, 14, and 88. And I want to let's say I want to do something to all of those items in the list, like I want to multiply each of those items by 2. So a more realistic example might be something like a list of prices, and I want to apply some kind of percentage reduction to all of the prices in the list. But for simplicity, I'm just going to multiply each of those values by 2. So you can see here, if I try and do this in Python by simply writing the name of my list, nums in this case, and multiplying it by 2, instead of it multiplying each of the elements of that list by 2, it actually repeats the list twice. So this is not the kind of behavior that we were typically expecting. So in a language like Python, we'd have to use an extra library to get that vectorisation type of behavior. So in Python's case, I can import the NumPy library, and then I can pass my list into an NP array. And then when I multiply it by 2 or divide it by 2 or do some other calculation, it's going to apply that to every element in that data structure. If we look at the equivalent in R, so we do the same thing, we create a nums vector in this case with the same values as we just had, we can straight away just multiply it by 2 and get the desired output. And that's because R was designed for statistical computing. So with that in mind, it makes sense that people are going to want to do things to, data frames, matrices, vectors, and other structures, because it's quite common to do things like, for example, find the mean of a row or a column, or apply some other calculation or function to a table, matrix, data frame, that kind of thing. So that was built into R from its inception, as it was designed for statistical computing. Python is a more general language. You can make games in it, you can make web servers in it, so it's more broad. So it doesn't, although you can mimic that behavior in Python as you've just seen, it wasn't specifically built for statistical computing like R was. So in this video, I'm going to explain how the apply function works, how it relates to iteration and vectorisation, and demonstrate it with a few basic health-like examples. So again, iteration is this idea of repeating an operation a number of times. So let's take a look at a more concrete example. So let's have a look at a matrix in R, which we could use to represent data. So in this case, perhaps patients, where each column contains some physiological measurement. So I've got an observations matrix, and in here I'm going to specify some values for some different patients. So let's say 3 or 4 different patients, and they're going to have perhaps their heart rate and their systolic and diastolic blood pressure, for example. Then what I'm going to do, just to make it a little bit easier, is I'm going to rename the columns. So rather than using the numerical values, I'm going to give them labels. So I'm going to give them heart rate, systolic BP for blood pressure, and diastolic BP. So I'm just renaming the columns of the matrix with labels instead of numbers. And then we can output that and see what that looks like. So here, each patient has heart rate, systolic blood pressure, and diastolic blood pressure. So let's do something fairly typical. Suppose we want to calculate the mean measurement for each patient. So we could do this with a for loop, and indeed in most programming languages that's how you would do it. And we can do that in R as well. So the first thing I'm going to do is I'm just going to make sure that all of the values are numerical. So I'm going to use the numeric function to make sure that all of those observations are in numerical format. And then I'm going to use a for loop. So I'm going to use I as my loop counter, and I'm going to loop over the number of rows, n row, in my observations matrix. And then for each of those, I'm going to calculate the mean for that particular row. So the loop goes through each row in turn, calculates the mean, and stores the results. This is what's called explicit iteration. And you can see the index, the loop counter I, it changes every time we go through the loop. So everything between the opening and closing braces, the squiggly brackets, is repeated in the loop that number of times. And it works fine, it's clear, and it's there's nothing wrong with that code. But Python has, R has a very specific way of managing these things itself through these, what we call these apply functions. So essentially R allows us to express this type of repeated operation more concisely with these apply functions. So the same calculation, the same thing we've just done using a for loop, we could do with the apply function. So we could create a variable called patient means. We could then use the apply function, and here we pass in the data that we want, so our observations matrix. We set the margin to 1, and then we set this variable fun to mean. So, and then we can output what that does. So just to break that down a little bit, what's actually going on. So the first argument in the object is the data that we want to work with, or the object, in this case a matrix. The margin argument tells R which dimension to operate over. So the options here are 1 and 2. So a margin of 1 applies to rows, and a margin of 2 applies to columns. So if you want to do things row wise, you use 1. If you want to do it column wise, you use 2. And the fun argument stands for function and specifies a function that we might want to apply. And again, R has inbuilt functions like mean, sum, and so on, but we could also apply our own functions as well if we wanted to. So what the code's doing is it's saying for every row in our observations matrix, calculate the mean for that row. So conceptually, the apply function is still performing iteration. It's repeatedly applying a function to different parts of an object. The difference is that the iteration is expressed through a function rather than written explicitly in the form of a loop. And you can see if we change the margin to 2, so this time we're doing it by column instead of by row, the function will operate on each individual column. So that would give us the mean heart rate, mean systolic blood pressure, and mean diastolic blood pressure across all of the different patients. If you can't remember the difference in 1 and 2 for rows and columns, one way you could try to remember this is that rows are the first dimension of a matrix and columns are the second dimension. So we've looked at an example using an inbuilt function in R, but we could actually use our own specific function as well. So we're not limited to the built-in functions like mean and sum and standard deviation and the others that R provides, but we could create our own function completely. So let's say, for example, we wanted to calculate something called the pulse pressure. we could actually write our own custom function to do this. And the pulse pressure is just derived from essentially taking the systolic blood pressure and minusing the diastolic blood pressure from that to get the overall pulse pressure. So we could define a function to do this that works on a single patient record. So here we create a function, we're going to call it calculate pulse pressure. It's a function and it's going to take in patient as an argument, and then it's simply going to minus the diastolic blood pressure from the systolic blood pressure. And now we've written that function, we can actually apply that function with the apply function to each row in our data structure. So for example, we could create another variable called pulse pressure. We can then use the apply function. Again, we'll pass in our observations matrix. We'll set the margin to 1. And this time for the fun argument, the function argument, we're going to use our own function, calculate pulse pressure, that we created earlier. And then we can output this and see what the result of that looks like. So instead of making a separate function and then linking to it in our apply function, we can also use what's known as an anonymous function as well. So we can basically implement our function directly in that code block if we wanted to. So here, if I get rid of the function call and actually set the function manually here, so I can write the function as part of the apply function here directly as well. So I could make it a separate function if it's quite complicated, then sort of link it, or I could sort of write it in place here inside the apply function itself. So this we tend to use those anonymous functions when a calculation is pretty short, pretty simple, and only needed in one place. If you're going to use it in multiple places, or it's maybe a bit more long and complex, having it as a separate function and then referring to it there is probably more efficient. So you can also pass in additional arguments as well into the apply function when it's being called. So lots of data sets, health data is no exception, often contain missing values. So in R, missing values are often represented with NA. So let's take a look at a different example here. Let's say we had some temperature data. So we've got another matrix. This time it's full of temperature readings from several patients, but it also has some missing data in the matrix represented by NA. So we've got, in this case, we've got 3 rows of patient data with a couple of missing temperature values in there. Now, if we try to calculate the mean, for example, in R with any NAs, we're going to get NA in the output. So we need to fix this. So first of all, I'm going to just rename the columns again, just to make it a bit clearer. So I'm going to label them morning, afternoon, and evening. So these are temperature readings taken at 3 different points throughout the day. So if we calculate the row means directly, the missing values will produce NAs. So if we've got any NAs in the data, then the row means are going to be NA. So this is an example of where we can apply additional arguments here as well. So in the apply function, I'm passing in our data, temperature data in this case, setting the margin to be 1, and then the function is going to be mean. And then you'll see if we run this, we actually get the NAs in the output. So we can pass in an extra argument, na.rm equals true. That means remove NA values we can pass that in to the mean function as well. So if we modify the code slightly, so the same code here, but after the function we put a comma, and then we put any arguments that we want to add to the function itself. So we're passing in the NARM argument to the mean function here and setting it to true. And now when we output it, it will remove those missing values and calculate the mean. So that extra argument is passed to the mean function each time it's called. So one question people often ask is apply vectorized? So this is where the terminology can get a little bit confusing for some people. It's often the apply function and its derivatives are often described as an alternative to using loops, but not usually vectorization in the strictest sense. So a vectorized operation works on an entire vector or array without us explicitly processing each element one at a time. So we could take a look at an example of a vectorized operation here as well. So let's say we wanted to look at the heart rates. So we could get a variable called heart rate, and then from that we can extract the heart rate column from our observations matrix, and here we can output any heart rates greater than 80. So this is using vectorization to do that. So in this comparison, operates on the complete heart rate vector. And we can do that with pulse pressure. So we saw how we could calculate the pulse pressure earlier. We could also do this directly using vectorized subtraction. So here we could create a variable called pulse pressure vectorized, and we could simply set it to be our observations systolic blood pressure column minus the observations diastolic blood pressure column, and then output that. So that is a vectorized version of doing the same thing exactly. So it's more directly vectorized than the earlier apply function example that we saw. But the apply function still divides the data into rows and columns and then applies the function to them repeatedly. So it's like a kind of wrapper for, doing those explicit iterations with things like loops. So a useful distinction is that a for loop performs explicit iteration, the apply function performs function-based or explicit iteration, and vectorized code operates directly on complete vectors or arrays. So in the grand scheme of things, they produce the same result, but they express computation differently. So under the hood, behind the scenes, how they're working is working slightly differently. And there might be at scale some performance advantages to using one over the other. But for most cases, it's just whichever method works best for your given situation. So we can look at a more concrete example of doing the pulse pressure in 3 different ways. One, using that explicit loop, where we, again, we'll convert everything into a numeric value in our observations matrix. Then we'll use a for loop to loop over our observations, and then for each of those records we're going to perform the calculation, so to minus the diastolic from the systolic, and then put that in our pulse pressure loop vector. So we're storing this, doing this through explicit iteration, if you like. And then we can look at the same example using the apply function. So same thing again, we create pulse pressure apply. We use the apply function, we pass in our observations, our margin 1 because we want it to work on rows, set our function, and here we carry out the same calculation, minusing the diastolic from the systolic. So we have pulse pressure vectorised, and that's simply the observations systolic blood pressure minus the diastolic blood pressure. So 3 different ways of doing the same thing. And we can see that all of the 3 results are equivalent as well. So for this particular problem, I would probably use the vectorised approach. It's just simpler, less lines of code, and probably the clearest in terms of what we're doing. It directly describes the calculation that we want to perform. But different situations, different things might be more appropriate. So when the operation on each row is more complex, the apply function may be more convenient. So let's take a look at a slightly more complex health example. So suppose we want to classify patients using both their systolic blood pressure and their heart rate. So this is for demonstration purposes. Obviously, we'll create a simple rule. It's not to be used for clinical decision making. It's just a programming example only. But we'll make a rule where we want to flag the patient, say if their systolic blood pressure is at least 140. So that's the top number in their blood pressure, or we'll flag the patient if the heart rate is greater than 90. And again, you could set whatever rules you wanted. So it's not a clinical decision rule, as I said, it's just a programming example. So we could write something like this in order to implement that process. So we could say flag patient, and then we could create a function, and then in the function we're going to have a variable called high systolic, and we're going to set that when the systolic blood pressure is greater than or equal to 140. And then high heart rate is going to be defined as a heart rate greater than 90. And then we're going to say, we're going to return high systolic, and the 2 bars means or. So high systolic or high heart rate are going to be returned from that function. So the 2 bars are or. So one or the other is going to flag the patient. And then we can use the apply function to apply this to all of our patients in our observations matrix, for example. So we could create a variable called patient flags, use the apply function, pass in our observations, margin 1 because we want it to work on rows, and then set our function to our flag patient function. And then we can output that to see which patients were actually flagged as being relevant. So this is a bit more of an expressive example showing how apply can be used. So you create a function that describes what happens to one patient, and then you use apply to handle that repetition across multiple patients. And of course we could use vectorization to achieve the same kind of thing. So here we say patient flags vectorized, and we simply say the observations are systolic blood pressure greater than or equal to 140, or observations where the heart rate is greater than 90, and we use a single bar because this is a bitwise or bitwise OR in this case. So again, the vectorized version is pretty compact, but the function-based version will probably be easier to extend if the decision process gets more complicated. So you can see there's trade-offs to using these different approaches. Just a thing to mention about data frames, the apply function is designed primarily for things like matrices and arrays. So if we pass in a data frame to the apply function, R will convert that data frame into a matrix. And that matters because if a matrix usually contains one underlying data type, so all of the elements in it are they're all numbers or they're all characters, that kind of thing. So just to show you what I'm talking about, if we create a simple data frame of patients, so let's say we've got a few columns. We've got a patient ID column, we've got an age column, and we've got a heart rate column, and then we've got some column describing that they're a smoker, which will be true or false. And let's just put some values in for 3 patients. So if we were to use the apply function on this data frame, then we might end up with some unexpected behavior. So the presence of the character data in the patient ID can cause the entire object to be converted into a character matrix. So text data essentially. And that can lead to unexpected behavior going forwards. So for mixed type data frames, there's extra functions like lapply and sapply and vapply and additional tools. So I'm just going to finish by giving you a little information about some of those other apply functions that you're going to see, just to show you kind of what they apply to when I finish the video. So these are often called or referred to as the wider apply family. So the base R apply family contains several related functions, and they work on different data structures and sometimes do slightly different things. So for example, some of them work on groups of things, some of them work with factors, some of them work with matrices or data frames, and so on. So in future videos, I will delve a little bit more into some of the different ways that you can structure your program, some of the different tools that are available to you through languages like Python and R. If you're interested in learning a little bit more about programming, so perhaps for developing your skills in coding to do things like AI engineering, machine learning engineering, learning more about data analytics for data analysis or informatics or data science, then I've written a couple of textbooks, one on programming and one on mathematics. They cover the fundamentals of both of these topics and don't assume any prior learning. So I've written them really for people coming from a health and social care background that haven't had the formal kind of maths and computer science training that people with the engineering kind of background get. So it doesn't assume any prior knowledge or awareness of any of those concepts. It starts very much with the foundation, but the examples are in both Python and R, so you can choose whichever language you prefer, or to look at how the two languages do the different things. There's also additional chapters on things like data visualizations and software engineering practices, things about building front ends using databases. So they're quite, it goes into quite a lot of detail. There's plenty of examples and quizzes with answers and solutions in the end, and different case studies as well to help you with your learning. If you prefer something more digital, then I have an online platform which has various courses. There's a free course on learning to program using Python, specifically with a healthcare and a data science focus. And that's completely free to access. So it's got lots of videos and text example code blocks you can run, and quizzes and things to help you to learn the fundamental concepts. At the moment it's only available in Python, but there is an R version coming soon for that platform, as well as other courses as well.